Okay. Good evening, all of you, and we are going to start this session. And today we will discuss about new method based on Taylor series, which we can use for both initial value problems as well as for boundary value problems. And this will help you to solve many type of problems and very quite easy to implement it to use to find out some numerical solutions and visualize our findings. Some basic concepts are required. Many we have already discussed in the very beginning in during the sessions, first eight sessions, essentials, MATLAB essentials for numerical methods. So first I need to share my screen and then yes, I hope MATLAB, this my window is visible to all of you. My screen is visible. So this is a little bit information about the Taylor series method for initial value problem and boundary value problems and how we can use this power series, this Taylor series method to find out the solutions for both type of problems. So the Taylor series method can be utilized for solving both initial value problem and the boundary value problems in differential equations. These methods rely on approximating the solutions using Taylor series expansion and then truncating these expansions to obtain approximate solutions. So here we have some steps how we can implement these. So the initial value problem, we have d upon dx is equal to fxy, and with the initial condition we have y x naught is equal to y naught. So the Taylor series method approximates the solution yx by expanding it around the initial point x naught. The general approach involves computing successive derivative of yx with respect to x at x naught and using them to construct a Taylor series expansion. And typically the expression is truncated at some finite order to obtain a usable approximation where sometimes we need to choose fourth order, third order, fifth order, depending upon the accuracy of the solution. So all of us, we are familiar about the Taylor series, which is presented at the space yx is equal to y x naught plus x minus x naught, y dash x naught plus and so on. So this is very familiar Taylor series, and by using this we can easily find out the solutions of initial value problems as well as boundary value problems and truncate the series. Retain term up to certain order n based on desired accuracy. So according to the desired accuracy, we can truncate the series and according to that, we will consider the order of the given by using this power series, Taylor series. Okay. And then what we need, we have to solve the coefficients. Okay. Obtain the coefficients using differential equation and initial conditions, and also when we have the higher order or second order differential equation, in that case sometimes to find out in the case of a boundary value problem, okay, we need to find out the interior points, and in that case we need to apply central difference also, which already we have discussed in the a few last lectures. And after that, we will evaluate, compute the values of the approximate solution at the desired point. And these four steps we need to follow to find out the solutions of initial value problem. And corresponding to this, we have a few steps for the boundary value problems. And here is the detail how we can use Taylor series for boundary value problems. So we have this is the differential equation of second order d to y upon dx square is equal to fx y and y dash. Okay, and subject to these are the boundary conditions. On the left end point we have ya is equal to alpha, and on the right end point we have is yb is equal to beta. We have this interval. So this is the left boundary and this is the right boundary condition. And Taylor series method can still be applied, and but it involves expanding the solutions around both boundary points A and B. The process is more involved compared to initial value problems due to the presence of boundary conditions at multiple points. So here you can see how we can apply. We have to apply this Taylor series expansion at both the points A and B. So we have yx is equal to ya plus x minus a y dash a and x minus a square upon 2 factorial y double dash and so on. Similarly, for the right end point, we can expand the given function yx is equal to yb plus x minus b y dash b plus x minus b square upon 2 factorial y double dash b and so on. After that, we need to construct the system of equations as I told you that. And yes, so after that, after establishing these two equations, we need to construct a system of equations, use the boundary conditions to form a system of equations for the unknown coefficients in the Taylor series. And then we will solve the system of the equations obtained in the step number 2. And at the end, we have to compute the values of the approximate solution at the desired point within the interval AB. Okay, so these are also desired for the consideration while applying this method. Convergence, we need to analyze also the convergence of the Taylor series method depends on the smoothness of the solution, and it may not converge for all differential equations, especially for those with singularities or discontinuities. So keep in mind while using this method, okay? And uh, a higher order Taylor series expansion provide more accurate approximation, but require computation of higher order derivative, which can be computationally expensive, and sometimes we have some challenge. And then after we have the truncation error. The series introduce truncation errors which must be controlled to obtain accurate solutions. And at the end, we have the stability or numerical stability. Care must be taken to ensure numerical stability, especially when computing higher order derivative or solving the system of equations for boundary value problems. So this is all about the basic information how we can use the Taylor series to find out the solution of initial value problems as well as boundary value problems. Taylor series method offer a powerful approach to solving differential equations numerically, especially when combined with other techniques like finite difference or finite element method. However, their practical applicability depends on the specific characteristics of the differential equations and the problem at hand. And also I will let you know sometimes when we have the system of equations or to find out the second order or third order derivative, sometimes we can use finite difference, and most probably we will use central difference to establish the system of equations as we do for during the problems by using finite difference method, okay, for boundary value problems. So in the same way, we can establish the equations for boundary value problems if it required. So now, one by one, we are going to discuss here the methods. Just 1 minute. Okay, yes. So this is not required, and come to this one. So I have created 2 folders and several examples are there. So these are the examples associated with the initial value problems, and very quite easy. Yes. So in the very first example, we are using Taylor series method, okay, to solve the initial value problem. And here the problem which we are choosing is, just 1 minute, I have to choose Epic Pen also. 1 minute, please. 1 minute. Okay. Yes. So here we are choosing a very simple first order differential equation, which is y dash is equal to minus 2y, and the initial condition we have is y0 is equal to 1. So one more thing I let you know, Taylor series is also inbuilt function in the MATLAB, and we need not required to create this Taylor series expression or not required to write a program to implement. Just we need to call this function from the MATLAB. Okay, so here we have these are the initial conditions. T naught is equal to 0, y naught is equal to 0, and the final value at which we wanted to calculate, we want to find the values in this interval. So this is the initial value and this is the final point. So for T final is we have 1, and the step size we are choosing is 0.1. So before implementing, we need to define symbolic variables, and I hope you are familiar about all these symbolic variables. If not, we can once again discuss about these symbolic variables. Yeah, see here I have also created the separate file for the basics which are required in the present discussion. So if you want to create the symbolic variable, then we have to use sims. Okay, if you are writing CLC and clear CLC, so you can see workspace there is no variable and no value exists. Okay, if you want to write any equation, sine x, okay, and when you will enter, you can see that there will be error because x is unrecognized function or variable x. So what we have to do, we can declare the symbolic variables. Say I want to use x and y, and it is t also. Okay, now I can easily write any function. F is equal to I have is sine x, and for the symbolic computing, we have to declare the variables, and then after we can easily use them. And if you want to differentiate diff f, and when you will enter, and you can see that the derivative of f function we have is sine x. And if you want to differentiate for the second order or third order, then how you can do okay, we can check once again if we can follow the Python code f comma 2. Yes, so this is the second order, and if you are using here 4, then yes. So in this way, you can use you can find the first order, second order, third order, and fourth order derivative. But in the case of partial derivative, because f will involve more than one variable, in that case, we cannot do in this way. Okay, but we can take higher order partial derivative by using the diff function also. So here we need only this type of calculations are required in the present discussion. And also we have sub function. You can see here subs function used for substitution. So here you can see we have sims function, sims variable a and b, and subs function is used here in the expression a plus b. And what is the meaning of a comma 4? First execute these two statements and see, run this section. Yeah, you can see that the value of a is substituted in a plus b, which is b plus 4. And similarly, if we have this expression and you are using subs function, okay, and but the value of a product b is 5. The value of a product b is 5, and here is a product b square. So when you will execute this statement, and run this section, yes, so ab square, the value of ab is 5, so the value of this expression we have is 5b. And similarly, we have several more examples. You can check them. Okay, here is we have x by a and x plus y 1. So this will simvar. This will declare the first variable. Okay, when you will execute, check it. So the first variable is x, and here we are using subs replace x with a. So when you will use at the place x plus y comma a, so x will be replaced with a. Yeah, and similarly we have these are some few examples for symbolic function. And yes, if you can also create a function involving two variable x and y by using sims. Okay, see here we have f x y. F is function of two variable, and after defining this function you can easily write any function of two variable. Here you can see fxy is equal to x square y. Okay, and you can substitute the value, or you can compute the value x equal to 3 and y is equal to for the above function. When you will execute, and you can see that the value is 18. Okay, so these are some basic substitution and symbolic mathematics which is required in our present example. Yes, come back. So here what we are doing, first we need to declare the variables. Sims ty is the differential equation involve two variable t and y. So this is the function, dy upon dx is equal to f ty. Okay, so this is the function handle. F is equal to, simply f is equal to minus 2 ty. Now we want to expand by using the Taylor series. So these are the value which will be expanded by using Taylor series, or Taylor series function will be stored at this place. And here y and t, and then we have expansion point, a note, and order 4 we are using. And along with the just 1 minute, at this place must be f. 1 minute please, I want to check. Okay, so here is expansion point is t note about which we want to expand. Okay, and order is 4. We can change this order, but the point at which about which we want to expand is t note. The given point is t note, and after that we need to compute first order derivative and second order derivative which is involving in the Taylor series up to we need to compute here. So diff f comma t, this is the first order derivative, and this will give us the second order derivative. So how we are using, this is the first order, and again when we use at this place diff f prime comma t, because this is the f is involving two variables t and f, t and y, but we need partial derivative with respect to t. That's why we are taking first order and second order, and the syntax, follow the syntax. But as we discussed previously, for the first order, second order, third order, by using the numerical value, we are not able to use at this place because this is the partial derivative. F is function of t and y. That's why for second order we are not able to use directly by using the numerical value. So that's why first we need to differentiate f with respect to t. This is the first order derivative, and again use the same process to get the double derivative. F double prime means second order derivative. Okay, so these orders which are required we can compute, and then after we need to compute the values at the initial points. So what we do, f t naught, y naught, these are the values when we have t naught and y naught. So subs function is there. Subs function is there to compute these values at t naught, y naught. See subs, and here is the f function. Ty, we want to substitute the values of t and y, and that of those of are t naught and y naught. But t naught and y naught are given at this place. T naught is equal to 0 and y naught is equal to 1. Okay, and similarly for f prime, similarly we will use f prime. We will get the value at t naught and y naught, and then we have the same approach, but at the place of f we have f prime, and these values we need to pass through the f prime function, and the values of t and y are t naught and y naught. So these are the values of ty. Okay, so the initial points has been applied. Now we need to compute the solution using the Taylor series. For that, t values we are choosing from t0 to t final. Okay, so initial point is 0 and the last point t final is 1 and h is 0.1. So t vector will be generated at this place, and in the second corresponding to this we need to generate 0 vector, and the length of t values and y values must be equal. Okay, and now we have the first index is y naught, so we need to apply initialize the loop at this place from the given initial condition. So y values 1 is equal to y0. So the first index we have is here, but now we need to compute the other values by using this initial condition. Okay, so the loop will start from 2. First index is here, second index will start from this place, and this value will be used at this place. Okay, so index will start from 2 and up to the length of t values, and note this point very carefully. And after that we have this is the Taylor series. Okay, see here, so this is yx naught, then y dash, and then y double dash, but remember that y dash will be equal to fyt. In our case, this will be fyt. So here you can see this is the y naught, then this is the first prime into h, then we have this is the next second prime, okay, into h square upon 2. So the series has been used at this place, and then we all the values will be computed by using this Taylor series and will store at this place. Then after we can easily plot the solution, and here is t values, y values, and this is the marker, x label, y label, and title, grid on. So when you will execute this sequence of statement, we have this graph. Okay, so now if you have any question, yeah, yes, please.
Good evening, sir.
Good evening. How are you?
Fine. In the Taylor series here, shall you share the screen?
Yes, I can share the screen. Yes.
Yeah, in the Taylor series here in the second term, this is the first derivative. Why you are wrote here double subs? Yes, this term.
Double. Okay,
Yeah.
okay. So in MATLAB, the double function serves to convert variable of other data type into the double precision floating point numbers. Okay, sometimes when you will compute the values, sometimes will be floating, and just to convert the variables in the other data type, we are using double.
Okay.
Yeah.
That is the reason.
Okay. So in the code, I already put at this place so that when you will get this script file, this will remind you the meaning of double function. Any more question, please?
Thank you, sir.
Great. And similarly, we have one more example, and yes, come here. We have at this place y dash is equal to y minus t square plus 1, and this is the initial condition we are given, and these 3 steps we need to follow, and will help you to use this Taylor series to find out the expression of this initial value problem. And quite easy. First, what we do, first we need to define ODE is function handle. Then we iterate over each step, computing the next value of yt using the Taylor series expression up to the second order, and then we plot the approximate solution over the specified interval. So these 3 steps need to follow to implement Taylor series. Okay, so here you can see this is the initial condition, initial time, then this is the initial value of y, this is the final value of time. Okay, and h we are choosing 0.1, and here we are using function handle. In the previous example also you can use function handle, there is no difference. Okay, but Here we declare the symbolic variable and then after we use, but in the case of function handle, you can directly use in this way. Now the rest other steps are same to use. Here is t values, t node to t final, and these are the y values. And you know the length of t values as well as y value must be equal. And this is the initial index of y values. And the loop will start from 2 to the length of t values. So these are a similar type of steps, and here you can find this is the y prime. Y prime means first order derivative, and this is the double prime means second order derivative. Okay, y dash we are given the function y dash will be equal to f t y. Okay, and y double dash will be equal to, this is the, by using the definition of a derivative. Okay, you can easily write as, see, by the definition y double dash can be written as limit h approaches to 0 and y dash 0 sorry y dash x naught. Here is x naught plus h, and then y dash x naught upon h. But you know y dash is equal to f t y. Okay, y dash is function of t and y. So where when you will use this value at its place, in the place of y dash you will use f t y. So this above expression will be converted in this form, and you can do in very easy way. Okay, so after getting y prime and double prime, then you can compute the next value of Taylor series by using the series expansion. Okay, so here this is the y value, this is the first prime, and this is the double prime. Okay, both the values are computed at its place, and then we are using here and here. Okay, so the values will be updated and will store at this place. And now we have the step to compute to plot the graph. Okay, so these are the same statement to plot the graph, and when you will execute, you can see the visualization of the solution of the given initial value problem. I think there is no question in this discussion. If you have any problem, please feel free to ask. I think it is very quite simple. Is it clear?
Yes, sir. Yes.
Okay. And in the third example also, we have this example, y dash is equal to t square plus y and initial condition. So these are the same statement, and here we are using sim ty, and Taylor series we have is third order. We are choosing at the place, and the other steps are same. We need to compute the values f t naught y naught, then f prime t naught y naught, and the double prime. Okay, so all the values we are computed at the space, and then after we use the for loop to get the solution. Okay, so here we are using third order. We are using, yeah, third order series. So we need these values. As you can see here, this is y, then you can see here is ft naught y naught, which is y dash, and this is y double dash, and here is y triple dash. Okay, so this is the complete Taylor series. But the most important thing is to compare the syntax, how we are converting all this. And you know the purpose of the using three dot sign. What are the meaning of these three dot?
Means continuous, continuous.
Yeah, continuous. When we have a very long statement and for the continuity, and we need to break that, that's why we are using these three dot. And the example is very quite simple. And here are the same statement to visualize the result. And when you will execute, we have this very smart plot is here. So this is all about initial value prompts, and now we are going to discuss about the boundary value prompt. Okay, so boundary value prompts are like similar type. little bit there is difference. Yes, two examples I choose at this place. For this one, I am using okay. I select here two examples. Yes, and both the examples are very quite interesting. So here the Taylor series method for boundary value problem we can use, and these are the few steps which you need to follow. First, formulate, write the given ODE y double dash is equal to f t y dash along with the boundary conditions, and then Taylor series expansion, expand the solution yt around the each boundary condition as we discussed in the beginning, left boundary as well as for the right boundary. Okay, then match the expansion at the interior point and formulate the system of equations. Use the matched expression, formulate a system of equations. And for the system of equations, sometimes we need to use finite difference method also. Okay, keep in mind. Then we have solve the system of equations to find the coefficient of the Taylor series, and at the end use the computed coefficient to construct a solution yt. So here is one example which by using the same we can easily find the solution when we have this type of differential equation with the boundary conditions. So here we have y double dash is equal to minus 2y, and left boundary is y0 is equal to 1, and right is y1 is equal to 0. So here we are defining the parameter in the beginning. Number of interior points we have is 100. These are the only interior point except the boundary points. Okay, so the total number of point will be 102, and combining the interior as well as boundary point, we have total number of point will be 102, but the interior point we have is 100. So the step size for we have is h is equal to 1 upon n plus 1. This will be the step size. Okay, and t values we have 0 to 1 depend upon this h. This will be for interior points only. Now, first the boundary conditions, whatever we are given, this is the left boundary, y naught is left boundary. You can write here, this is the left boundary, and this is the right boundary. Okay, this is the right boundary. And then after we need to expand Taylor series. So we are going follow the same approach. Since ty is equal to f minus 2y, and here is y Taylor. Okay, this is the Taylor series, and yt expansion point t naught order for the same approach is here. So for the same, we need to compute here f prime and double prime, first order derivative and second order derivative. Okay, for f, and then we need to evaluate at the boundary points. So this is the left boundary values. Okay, note very carefully f t y, and these are the left boundary t value 1 and y naught, and t f t1 y n1. N1 means right end point. Okay, so we will calculate here the value at the right end point for f function. Okay, so these are the boundary values only. Now we compute the solutions using Taylor series. Okay, and here is a is equal to what is a? A will be the matrix, because when you will apply, we will have the system of equations, and in the system of equations the A matrix will be of order n plus 2. Okay, and this is the B vector. The solution will be like a y is equal to B. So this is the A matrix, the coefficient of the Taylor series, and this is the B. Now the boundary conditions, this is the A11, which is 1, and this is the end right end point. This is also when you will apply the boundary conditions and we will have the matrix. So the A11 element will be 1 and also the end point. At the end point means when we will have n plus 2 and n plus 2. Okay, that will be also equal to 1. And B1 is y naught and B end is y and 1. Uh, you know how you can get these values? When you will apply the Taylor series and you will have system of equations for all these points for the interior point. Okay, so when you will calculate the coefficients, okay, A11 and a n plus 2 n plus 2 will be 1, and after that we need to calculate the interior points. This is very little bit typical because as we do while using finite difference method, we have system of equations, we compare the coefficient, and then from that we have A matrix and B matrix. The same approach we have to use at the place because the Taylor series involve here first order and second order, okay, derivative, and for that you have to use you need to you can use finite difference approximation for second derivative at interior point. Okay, so by using the same we will have this value, these will be the interior points. Okay, so first you need to establish the system of equations, then you will compare the coefficient. But here just I have the code right here, but the numerical calculated part I did not introduce here. Okay, if you need I will provide you, but sorry, due to lack of time I'm not able to say I did not create the PDF file. So that was easy, but on the paper I do this work. But this is very quite simple. Just you need to apply finite difference approximation of the second order derivative at the interior points. As we do in the finite difference, same approach is need to apply at space. So here these are the interior corresponding interior point, and then after these are the BI value, double subs we need to compute. Okay, so then after we have y values are equal to all these will create the system of equations, and y values will be equal to a backslash b. This will give us the solution of the system of equations, and all will be the y values, and then after we can plot the graph. So this is the approach to plot the graph. So here you can see to plot 0 and t value is 1, and here y naught uh, these are for t. So 0 and 1. At this place we have only the interior values. Keep in mind these are only the interior values, but for the boundary value of boundary point, this is 0 and this is 1. Okay, and these are the t values, and corresponding to these this interval, y naught is corresponding to when we have is t0, and y values which we compute at this place is corresponding to the t values, and yn1 is corresponding to when we have is t equal to 1, and this is the marker, and other things x label, y label, and title, these are similar statement which we are using, and when you will execute this sequence of statement we have this solution. So this is the approximate solution using the Taylor series method for boundary value problem. Only the challenge you will have this part, only this part. Okay, you need to note this point very carefully, how you can get these values by using the finite difference for the second order. This is very important. This will take some time. Got it? Any question, please? Okay, no question. So this is the another approach for the same boundary value problem. But in this case, what you will do, formulate the equation, then you need to expand the series around this point. This is the same approach, and then after mesh the expansion and formulate the system of equation, use the meshed expansion formulate system. This is a little bit easy as compared to the this one. So then after we will use computed coefficient to construct the solution. So here is this is the left boundary, this is the right boundary. B is equal to 2 pi. N, we are choosing here the number of sub intervals 10, and this is the step size. H is equal to B minus A upon N. Okay, and here are the t values, y values. These are the similar step. These are the boundary conditions which we are given. The left boundary is 0 and also right endpoint is 0. Both are 0. Okay, and then after we have f is equal to minus y. The problem which we have is dy upon dt. Dy upon dt is equal to minus y. We are using the Taylor series expansion. First we need to create f prime and f double prime. These are same step. Then after you need to calculate the derivative at the boundary points. Okay, so this is f(a)(ya), left boundary point of function. This is the right boundary point, and this is the first order derivative at the left boundary point, and this is the right first order derivative at right boundary points. So these values are required as per our given conditions. Then after compute the solutions using the Taylor series, and the loop will start as we know 2 to length of the t values minus 1, because we have to exempt the right endpoint. That's why we have minus 1. Okay. Now for the coefficients, to compute the coefficients, we can take help the equations. Okay. See here, swallow function. We have numerous equations, and by using the same, we can use a swallow function here. This will solve all type of the system of equations. Okay. Subs function is here. Y Taylor series, value of t and t values will be equal to y values at I. So this is first equation, and so on. We will have this is the last equation. So we have the system of equations, and you will get the real value is true. So these equations, this system of equations will solve all the coefficients. Okay, and then after compute yt using the obtained coefficients. So here we are computing the y value and subs y Taylor series and the coefficient which are computed at this place. So in the Taylor series, we will pass or substitute the coefficients which are computed at this place. Okay, so this solve function will always solve the system of equations, but here we are solving for the coefficients. And when you will use at this place, the value will be computed at this place by using this expression. And yes, now we have the plotting. When you will execute, yes, we have this solution for this differential equation. So these are the two different approaches, and when you will use, there will be some challenge for the boundary value problem using the Taylor series. But if you will try carefully, this will be clear. If still you have challenge, you can discuss again with me. But the challenge is only for this first example. Okay, for this part. If you have used the finite difference, then there will be no challenge for this part. But also I will try to provide the PDF file after creating the same for this part, and I will upload there. Now, any question, please feel free to ask. Any question, please. All of you are very silent.
Good evening, sir.
Good evening.
Sir, in the starting of the lecture, you discussed about the method for where we can use these things. But you mentioned there was mentioned that sir, it can't be used for all the differential equations, especially where singularity is there.
Yes.
Yes, sir. What are the then other methods which we use for those differential equations where we have the singular type like that?
Uh, for the similarities, very critical question. Just 1 minute, please. 1 minute. Gangtak, your mic is unmuted. Please keep mute your mic. For the singularities, we can have involving singularities. We can have
Sir, can we remove the singularity from the code if we got the singularity at some fixed pointers? Because if it is, I think in my mind it will come at the zero, maybe.
mm,
For example, sir, for example, if we got the singularity of the system at zero, we can omit the zero from the code. Is it possible?
actually, the methods like we discuss finite difference method or finite element. These can be used to find out the solutions of this type of problems, because the methods which we are discussing for the numerical approach, this Taylor series based on the continuous function. So that's why we are not able to use this Taylor series for singularities involving in the differential equations. But finite difference method or finite element can be used.
And also, sir, I think discretization methods like that Euler method,
Yes,
Euler
yes.
method maybe.
Euler method may also be used, but we
Yes.
have to check where such type of the problems which are involving singularities.
Sure, sir, sure.
Yeah, actually, the thing is that there are various methods, and every method have their special accuracy, and error analysis are required before using. Okay, and according to the given conditions as well as the specialties and the error analysis, we can able to use these methods, because all type of methods have their special characteristic properties to use and to find out the solutions.
Yes, sir. Yes, sir. Actually, sir, I
Yeah.
gone through some papers and they mention that the singularity pointers, they omit the singularity point from the code. There was something like that in some papers. I gone through that.
Yeah, yes, because there are many problems in mathematics, and other things. Many challenges are there, but we can check it before using. which method is more appropriate or applicable.
Sure,
But
sir,
in
sure,
the case of Taylor series, there must not be the singularities. Only then we can apply.
Okay, sir. Thank you, sir.
Yeah. Yes.
Thank
But
you,
the
sir.
finite difference method and finite element, these can be applied for this type of problems.
Okay, sir. Thank you. Thank you.
Yes.
Thank you, sir. Thank you.
Along with we need to check accuracy and stability for the solutions also. This is also the essential part for numerical method. Any more question, please?
Sir, I also one request, please.
Yes.
Sir, for stability, what we have to do for stability of the method? What we have to do, sir?
Pardon?
Sir, to check the stability of the method,
Okay.
sir, what we have to do, sir, please?
Stability and error analysis we discussed during the Rangta method and the other method, and the same approach
Yes, sir.
we can use for Taylor series also.
Sir, could you please just give a rough idea about that, please?
Rough idea. I will come tomorrow with a rough idea.
Okay, sir. Thank you. Thank you, sir. Thank
Okay, actually, I have to write the code and then I have to demonstrate.
you.
Without
Okay, sir.
without the code demonstration, not possible. And
Sure, sir, sure. I
because
get
we
it.
have to introduce 5 examples related to the Taylor series, so for the timing, I skip this part. If it is required, error analysis, stability, accuracy, then I can introduce one more example for this part of analysis.
Okay, sir. I will also check the previous method. Okay, sir. No
Yes,
problem.
yes. If you
Okay,
can check the previous lecture when Rangta method and Euler method, in that case, we introduce both type of stability analysis as well as error analysis. And
okay, sir. Okay.
if you need, I will upload the error analysis for this method also.
Okay, sir. Thank you. It's okay.
Okay.
Thank you. Thank you.
Yes.
Thank you, sir. Thank you.
And any more question?
No,
Okay. Yes, Dr. Dinesh, namaskar ji.
namaskar, sir. How are you, sir?
Yeah, I am very fine.
It's a very interactive lecture. I thank you to you and thank you to all also with happy Holi.
Thank you, thank you, thank you, sir. And same to you.
Thank you.
Okay, dear friends, good night. Tomorrow we will join at the same time. And happy Holi to all of you. Good night.